pretty excited about working on, but I haven't actually done a lot of work on yet. So let's just say I have some preliminary results, and there's going to be a lot of introduction to this topic. So I guess our motivation for studying radioactivities in the solar system, there's lots of different questions that you can get from meteoritic data. And this is just, for example, if you look at the radioactivities that you get from meteorites, you can find out things about the timescale for formation of the terrestrial planets and even the formation of the formation timescales for the solar system. Also questions about the astrophysical environment in which our sun was born. For example, did a nearby supernova trigger the formation of our solar system? What about the nucleosynthetic origin of these nuclei? So by that I mean what sort of stars made the nuclei that we find in the solar system? And I'm interested in the last two questions, but I'm really interested in the last question. So I study stellar nucleosynthesis, so I really want to know what types of stars made those radioactive isotopes that we find in meteoritic data. So what sort of radioactivities do we find? Well, we find a whole lot with varying half-lives. So this is an example of some short-lived isotopes, including aluminum-26, calcium-41 and iron-60. So these have half-lives from anything from 0.1 megayears up to 1.5. We find, I'll show a table of some of the isotopes found in different meteorites in the next slide. But just to note that, so if we're trying to think about where these radioactive isotopes come from, and this is really my take on this story, I'm not really, even though these isotopes can give you lots of information about timescales of planet formation and all the rest, I'm really interested in where these nuclei came from. So stars are constantly replenishing the stock of isotopes in the galaxy. This is standard chemical evolution. And this can certainly explain the presence of long-lived isotopes, such as the plutonium isotopes, the uranium isotopes, that have half-lives, that have very long half-lives. But what about the short-lived isotopes? Chemical evolution, it's very hard to explain the presence of, for example, calcium-41 with a half-life of 0.1 megayears through these chemical evolution effects. So this led to the idea that there was some sort of local event in time and space that happened near our forming solar system. So they were either produced in the early forming solar system through spallation, or there was some sort of star that exploded.
But something like 0.1 megayear, that's such a tiny, tiny lifetime. The solar system formed billions of years ago. Wouldn't this thing have to be produced much more recently than the formation of the solar system?
Well, the idea is that this calcium-41 was inferred to have been present from meteoric data. It isn't present today. So it's the decay of calcium-41 that we detect in meteorites, if you see what I mean. So we inferred it to have been live at the beginning or in these solids that first formed. So there's like calcium, aluminum inclusions and chondrites and things. Yeah, because we have, I think they look for excesses of its daughter isotope. And so they find these excesses, and that's how they infer that there was more calcium-41 present than you would find, than they would expect, basically. Certainly the presence of short-lived nuclides is one piece of evidence that's led to the suggestion that a nearby supernova triggered the formation of our solar system. So this is just a summary of some of the, it's not a comprehensive list, but it's the summary of some of the short-lived isotopes found. So they go from increasing half-life, starting from calcium-41 to samarium-146. So I was showing the isotope, its half-life in megayears, the daughter isotope, so this is what it decays into, the reference isotope, so when we measure it in a meteoritic sample to measure it against this stable isotope, and then the initial ratio. So, for example, for calcium-41, the calcium-41 to 40 ratio was inferred to have been 1.5 times 10 to the minus 8.
Just out of curiosity, if it had just been, what would have been expected? If it had just been a little bit that's left over from...
A lower value. So I'm not sure what chemical evolution, if you just take, well, I think, say, for example, aluminium-26 is an example, because we observe aluminium-26 live in the galaxy today. We observe it from using gamma-ray satellites. And I think that, so the abundance of aluminium-26 to 24, I think that should actually be to 27 there anyway, I think that's a reference isotope, is about 5 times 10 to the minus 5. And this is much higher, so you'd observe, I'm not sure the number that's expected from chemical evolution effects, but it's much lower than, by a couple orders of magnitude, than what we have inferred to have been present in the early solar system. I'm not sure of that number though. So. It's kind of the life cycle of stars. So stars live and die, and they make stuff, and they, so like a supernova explodes, it injects stuff into the interstellar medium. Low mass stars, they have these winds, and these winds then enrich the interstellar medium with whatever products that star makes. And over the course of many stellar generations, the metal content, however you define metals, slowly increases with time. So the idea is if you look to the halo, which is very old stars, they have much lower, say, iron content than you observe in the disk of our galaxy. That's an example of a chemical evolution effect. So I've highlighted aluminum-26 with a half-life of about 700,000 years and iron-60 with a half-life of 1.5 megayears. I'm going to focus on these two for most of this talk, although I'm going to mention some of the other short-lived isotopes, and by short-lived I think anything with half-lives less than about 6.5, so palladium and up in this table.
The half-life doesn't say it was formed.
The half-life, that's just how long, that's just the half-life of that isotope. It just says, for example, that takes 3.7 megayears for a sample of manganese-53 to decay by, to reduce its abundance by half, essentially, right? That's just all it.
You'd like to know how, you could have had many half-lives and you end up with the initial ratio.
Well, there is a bit of modelling to find the inferred value, I suppose. So what they take is they have these plots of, I guess, stable isotope versus radioactive to stable, and then that's where the reference comes in, and then they plot on a line. So they take samples from meteorites and earth rocks and all sorts of things, and they have these lines that they can draw up, and then they go, okay, so back at the very beginning we infer that this isotope must have been that value just from taking all sorts of points. So there is a bit of modelling and extrapolation involved in that process. But I'm not an expert on the meteoritic side, just to point that out. This is just, how can I, anyway. Okay. Yeah, I'm not a geochemist, but.
What is the answer? How long before it's not much different?
Okay, so if we look to just a schematic cartoon of in the beginning, I'm not really going to, as I said, talk too much about the details of solar system formation, but just say that the giant molecular cloud that our sun was born from, it would have contained a whole lot of these radioactive isotopes from chemical evolution effects. So these would have in particular included the long-lived isotopes, such as plutonium, uranium isotopes, samarium isotopes, and these come from the chemical evolution effects. So these come from previous generations of stars. The short-lived isotopes, given the timescales for formation of the solar system, it's very hard to understand how these can be explained through previous generations of stars, and so this led to the idea that they were formed either through spallation reactions. So is there a pointer? There is a pointer. So maybe sometimes through when the early sun was producing many energetic particles, or they were produced by a nearby star that would have injected some of these isotopes. Okay. So there are two main origins to explain the presence of the isotopes. The first is stellar nucleosynthesis, and this is the one I'm going to mostly concentrate on for this talk. And the second is spallation reaction, for example, Frank Shu's X-Win model. I'm not going to talk too much about spallation, just to mention. So this is a cartoon showing. So this is a cartoon to show the X-Win model, or the ideas of what happened in the X-Win model. But I think the main point of this is that the X-Win model predicts that you had lots of energetic particles close to the early sun. This is where most of the spallation reactions would have occurred. So that means that the first solids that would have been formed closer into the sun, and these would have had higher amounts of radioactive stuff. So I guess the summary is that the X-Win model predicts a non-homogeneous distribution of the radioactive isotopes. That's, I think, the main summary of this cartoon. Whereas if you had a stellar nucleosynthesis contribution, you would have had a fairly homogeneous contribution of those radioactive isotopes, because they would have been injected into that giant molecular cloud, and I suppose they would have been fairly well mixed. So Frank Shu's X-Win model has a flow of material and radiation from a region near the sun, and this is certainly the likely origin for beryllium-10, which cannot be made in stars, it's only destroyed, and perhaps some portion of other isotopes, such as aluminum-26, calcium-41 and manganese-53. So I guess it can make the lighter atomic mass nuclei radioactive species. That's, I guess, the summary. There is a test you can do, though. If spallation did produce all of these isotopes, then if you look in the right sort of sample, and I'm not going to really go into details about what is the right sort of sample, but if you look into a sample, then all of these isotopes should be present. And so Kuljit Mahas in 2002 determined that beryllium-10 was present in samples of hibonite, but not the other species. And she concluded from this particular study that whilst beryllium-10 is produced by spallation, it can really only be produced by spallation reactions. It cannot produce it did not produce the other species, or at least it did not produce all of the other species. And certainly, if we look at the distribution of aluminum-26, it's found to be fairly homogeneous in meteoritic samples, and this would also not be the case if it was produced by spallation. And this is certainly one piece of evidence that stellar nucleosynthesis was responsible for making most of this isotope. Sorry? Yeah, most of the I think most of the meteorites that they take these really old carbonaceous chondrites, and I think most of them are I think they guess from asteroid material. I'm not sure where they're all kind of really stony rocks. So these carbonaceous chondrites are also very stony sort of meteorites. So I don't know if I don't think they're meant to come from comets. And these are the oldest ones that they find. They have lots of volatiles and lots of other things that suggest that they're old. And also, these have the highest concentrations of these calcium-aluminum inclusions that they think are the oldest, or the first solars that formed in the solar system.
Is there any evidence of the cometary material is there only in the IDPs? We sample them only in IDPs. We don't sample them in meteorites.
Okay.
So, and therefore, all meteorites typically come from the asteroid belt.
Okay. So for the rest of this talk, I'm going to focus on the stellar nucleosynthesis scenario. So if it was a star that produced the radioactive isotopes, what sort of star? Certainly the high abundance of iron-60 found in primitive meteorites points to a close supernova event. And there's lots of qualitative reasons that favour a supernova scenario. It can trigger the formation of the solar system, and it can easily account for the production of all the radioactive isotopes, with the exception of things like beryllium-10. No, you can't, exactly. It's only produced through stellar nucleosynthesis. That is also the biggest thing. Yep.
It's nothing heavier, it's small.
By mass balance, the chemical distribution of elements is such that as you go along higher atomic numbers, then the total abundance goes down. So you need enough targets to essentially spallate and produce the...
And also just to point out that the initial iron-60 to iron-56 ratio is still a little uncertain. So even though supernova fit qualitatively, the iron-56 to 56 ratio is fairly uncertain. And also, if supernova produce all of the radioactive isotopes, that is, all of the aluminium-26, 41, 53, etc., then the abundance of iron-60 and manganese-53 would be much higher than we find in meteorites. So the fact that it's not a quantitative match with the meteoritic data has led other people, in particular Jerry Wasserberg and his collaborators, to suggest that supernova are not an acceptable match to all the data. And it was this reason that led them to look for other sorts of stars. Now, iron-60 can be produced in other stars. It can be produced in low and intermediate mass asymptotic giant branch stars. And so we thought if it was a star that produced these isotopes, and it certainly was going to produce iron-60, then how do we decide between the two types? So within the stellar nucleosynthesis idea, there are two main hypotheses. The first, possibly the best qualitative match, is that all the short-lived isotopes came from one or more supernovae. However, the one that I'm going to explore in this talk is that the short-lived nuclides were explained by an AGB contribution plus also a substantial chemical evolution component. So if you like, this is what we consider an AGB plus supernova scenario. We like this idea because, well, there's lots of reasons that AGB stars are not... it's not so ridiculous that AGB stars contributed to the radioactive inventory of the solar system. We find lots of AGB debris in meteorites. For example, most of the silicon carbide pre-solar grains we find, so these are bits of stardust that condense in the outflows from stars. Most of these pre-solar grains, most of the silicon carbide grains came from AGB stars. Most of the spinel, and also much of the graphite and hibonite as well. This is just an example of a few different types of grains. This is a hibonite, this is a graphite grain. Both of those have heavy element compositions that suggest they came from low mass stars. So the other thing is that if we look at, say, the more massive range of AGBs, so this is the 3 to 8 solar mass stars, they have actually fairly short stellar lifetimes. We take a 6 solar mass star, it has half-life, so it has a stellar lifetime of about 60 million years. So these stars, they're not these long-lived one gig-year stars. These live and die fairly quickly. They're found in OB associations in the galaxy, so they also track the distribution of massive stars in the galaxy. So first, I think, before I go on to more details about AGBs, because we aren't going to give up on the supernova idea completely, so I'm just going to briefly review supernova nucleosynthesis followed by AGBs, and then maybe some ways to discriminate between the two ideas. So just to recap, these massive stars that explode as supernova are greater than about 10 or 11 solar masses. They go through all major burning phases in their core, from hydrogen through to silicon, with successive shell burning layers, as shown schematically in that diagram on the right. And they end their lives as called collapsed supernova, where the remnants are a neutron star or black hole, depending on the initial mass. Massive stars produce most of the, or I guess all of the alpha elements in the galaxy, so that's oxygen, neon, magnesium, silicon, etc. And they're also the likely site for the rapid neutron capture process. This is where you add neutrons so quickly that if you reach something that's unstable, it doesn't have time to decay before capturing another neutron. So this way you tend to make the heaviest elements, so uranium, thorium, etc. Aluminum-26 and manganese-53 are synthesized in large quantities in the supernova explosion, whereas iron-60 comes from the previous hydrostatic burning phases in the helium and carbon burning shells. How much aluminum, maybe I should say aluminum-26 and iron-60 do they make? Well, this takes results from Lamonji and Kiefi. You don't get much different results if you look at Weasley's models either. So this is showing as a function of initial stellar mass. This is the yield, so this is just the amount of, say, iron-60 expelled into the interstellar medium through the supernova explosion, and also the winds. So this red doesn't show up too well, but these red dots, these are the yields for iron-60. This is aluminum-26. The main point I want you to take away from this plot is the ratio between the two. So if we look at the ratio of iron-60 to aluminum-26, it's less than 1. So we're thinking, can we use these sorts of radioactive pairs as a way to discriminate between the two models? Because I'll show that AGB stars produce something that looks quite different to that. So just to recap what AGB stars are, these are stars with initial masses between 1 to 8 solar masses. So this shows the schematic structure of an AGB. This is the carbon-oxygen core from previous helium burning. There are 2 burning shells, one burning helium into carbon, another burning hydrogen into helium, and then you have this very deep hydrogen convective mantle. AGB stars are important because the helium burning shell is thermally unstable, and it flashes or pulses, if you like, every 10 to the 4 years or so. Why that's important is because it drives mixing between the core and the envelope. So it's a way of mixing stuff from the core into the envelope. The main things you mix are helium burning products, so carbon, and also elements produced through the slow neutron capture process. So this is opposite to the R process, so now you're adding neutrons much more slowly, so if you get to something unstable, it generally has time to decay before capturing something else. So you'd make the most stable elements that way. AGB stars are also important because they lose their hydrogen mantle that's been enriched in all this nucleosynthesis to the interstellar medium through these slow, dense stellar winds. So they're slow, 10 to the 15 kilometres per second, but they're very dense, so this is like 10 to the -4, -5 solar masses per year.
With the isotope bonuses, is that like the red curve? Is that are those features real, or just you aren't really resolving what's going on there?
I don't think they're probably real. I mean,
so it's probably just some kind of.
There could be something about. This could be. This is certainly the mass range where the Wolf-Rayet stars might start, since iron-60 is coming from the previous. It's being produced through previous hydrostatic burning. It might have something to do with the types of winds you're assuming. I mean, this is certainly the case here. I mean, this is using a different mass loss rate here, for example. So, because this is certainly this is the regime of the Wolf-Rayet stars up there, and these stars, these yields are all going to be affected by that, because you can get down to the helium burning shells in a massive star through Wolf-Rayet winds. So there could be some effects like that. But it's probably not real. I mean, there's so many uncertainties with these models where you choose your mass cut and if you computed enough models.
So other than the fact that it varies, the ratios vary with mass, it's hard to conclude.
I think so. I mean, all we're really interested in is the qualitative picture here that there's less iron 60 than aluminum 26. I'm not sure even. I mean, that's not the case up here, but these 60 solar mass stars and above are going to be so much rarer than these ones down here. So.
Can you not observe lines in actual AGB stars that are like today?
Sorry?
Can you, from observing AGB stars today, can
Yep.
you infer from the lines anything with radioactive lines?
It's yeah, you can. Well, some isotopes, yeah. So you can observe technetium. You can observe live technetium in an AGB star. That's one of the isotopes that you don't find present in the early solar system material, which is a bit interesting. You don't observe, from what I think you have some things going against you, because most of the AGB stars you observe in the galaxy are low mass stars. Well, first of all, it's hard you don't really know their mass, but they're probably going to be low mass AGBs. That's a 1 to 3. And as I'm going to show later, just in a slide or two, how much aluminum you predict to make in an AGB is a strong function of stellar mass. So you predict to make it more in the upper mass range, and you don't observe those stars very often. They're very hard to observe. So just because it's very hard to get a handle on a star's initial mass in the galaxy. And if you look to the Magellanic Clouds where we know the distance, so we can get the mass more or less, it's hard to know. Those stars are so far away, it's hard to get accurate abundance determinations. So you've got a number of things going against you when you look towards the stars you think can make aluminum. So just that's about AGB stars. So they have these thermally pulsing and mixing. And this mixing is responsible for making carbon stars. This is how you make single carbon stars. So this is showing results from a stellar model, 3 solar masses, revised solar composition. So this is time just during the AGB phase. So it's a very short-lived phase. Mass on the y-axis. So this is mass of the helium-exhausted core, hydrogen-exhausted core. This is the carbon-oxygen core. So this will be the remnants, the white dwarf remnants later. This is a hydrogen-rich mantle up here, and this is. And every time you have one of those thermal pulses, they're very brief bursts of helium burning. Some helium's converted into carbon, and the mass of this core grows. The mass of the helium-exhausted core grows. Every time you get a mixing episode occur, you have hydrogen. You have some. You have I guess if you want to think about it, the mass of the hydrogen-rich envelope moving into a hydrogen-depleted region. So each of these dips here is a mixing episode that mixes some carbon essentially to the envelope. So the star goes from the number of carbon atoms to oxygen atoms at the surface of 0.3 to a carbon star where it's greater than 1 at the 14th thermal pulse. That just shows that these stars, that this is how you essentially make carbon stars, how you make carbon, how you make its process elements. The more massive stars I find a bit more interesting. So these are the 3 to 8 solar mass. These also have these mixing episodes and thermal pulses, but they have these really deep envelopes that press down into the top of the hydrogen burning shell, and you can have proton capture nucleosynthesis in a very thin layer at the base of the envelope. This is called hot bottom burning, or envelope burning. It has a number of different names. This is interesting. The temperature, this shows a model for a 6.5 solar mass model of solar composition, and you can see that the temperature at the base of the envelope for this model, again scaled just during the AGB phase, reaches 90 million degrees Kelvin. So this is certainly hot enough to sustain the CNO cycles, then also the higher hydrogen burning chains such as the neon sodium chain and magnesium aluminum chains. So these can make things like sodium-23 and importantly aluminum-26. So just a summary of AGB nucleosynthesis, you have these brief bursts of helium shell burning, followed by mixing from the core to the envelope, and a longer interpulse phase, which is essentially just hydrogen burning. That's providing most of the luminosity. You have a low mass regime, what I'm going to call, this is a 1.2, say, to 3 solar mass. The mass range is not really that well determined. This is where you have just the mixing, essentially that changes the surface composition. So you have carbon mixed to the surface and S process elements. And then you have the intermediate mass regime, where you have, alongside the mixing, this third dredge-up, you also have proton capture nucleosynthesis. These stars have been suggested as being the main source of nitrogen in the galaxy. That may or may not be true, but there's some questions whether they can produce S process elements, and this is one side thing that I'm interested in as well.
Let me say something. So, in order to make one of these stars produce short-lived elements in our solar system, you've got to overcome two things with an AGB star. One is you have to put it very near to us, otherwise it will take forever to get here, it will have decay. And the other thing is that these things live longer than supernovas.
Yes.
You have to form them way before you form
Well, it depends on what sort of mass. If you're talking about an 8 solar mass star, or 7 solar mass, or 6, which is the ones that we're focusing on, they actually have lifetimes that are. Let's take that 6.5 solar mass star that I showed earlier. This has a lifetime of. Well, this is the total, essentially the stellar lifetime. This is where the star becomes a white dwarf. So this is a lifetime of 53 megayears. A 10 solar mass star has a lifetime of, say, 40 megayears. So there's not much difference between that. So these stars are also, they track the same distribution in the galaxy. So my 6.5 will track the same distribution in the galaxy as that 10 solar mass star. It would be found in the same sort of associations, if you like.
Yeah, but now you're trying to say that you want to have both supernovas and these guys contribute to the nuclear abundance of the galaxy, which means that's a spread. So in order for both of them to get here within 0.1 megayears, which is very short.
I guess so what we're interested in is so the very short-lived isotopes come from AGBs. Yes. So, but something like manganese 53, which has a slightly longer half-life, could come from a supernova.
Yes. Yeah. But now you have to invoke that, okay, these two things have to arrive within a megayear of each other.
Sure.
Okay,
Yep.
That's very short compared to the lifetime, even short compared to the difference of lifetime.
Yeah, sure. Yep.
So you have to arrange that this guy has to form, just enough earlier. This guy has to form exactly 10 megayears and be very nearby.
Sure. Yep.
Another supernova in the same molecular cloud.
Yep.
And so you have to adjust the lifetime information times of all these guys, such that they all arrive at our place.
Yes. Yep. It's true. It is a much more complicated scenario than just a supernova exploding. But the thing is that supernova if you take any supernova model at the moment, it just doesn't fit. And I know there's lots of problems with supernova models, but it's not that easy to explain. It's really actually difficult to explain the abundance, the isotopic abundances that we measure from these radioactive isotopes with any supernova model. It just cannot be done very easily without doing something that's almost as crazy as what we're suggesting. So in some ways, that's maybe been the main reason that's led other people to look at what other stars make. I mean, I think
what... Not so terrible in the sense of, in any case, the sun probably formed in a fairly massive cluster. Okay? And in a massive cluster, you're going to have, say, tens to hundreds of old stars. Now you got to have this range of ages for the cluster, for stars in the cluster, of order 10 million years or something like that.
In order for this guy to explode evenly as he did.
Well, once you do that, you're okay, because the AGB stars, there's a whole bunch of them all go together at the same time. So there'll be one guy popping off and another guy popping off and another guy. So that part isn't so bad, but getting a spread between the AGB stars and supernova.
That's a bit harder, yeah. I think we understand it's hard. I think this is just an exploration into a different idea to try and see if we can, without doing something crazy to our AGB models, can we try and make the models, can we compare our models to the data and see how it fits? I think that's what we're doing here. I think qualitatively, as I said, supernova is the best candidate, but it just, as I said, quantitatively there are many problems. So.
You need to leave all the Wasserberg stuff. That's
So on some level, he's a very convincing man. So.
Indeed.
You have to be within a parsec, essentially.
Had to be felt. So.
You all form a cluster.
It's not so much then.
Clusters, they're not that.
I mean, today we're separated. The typical distribution in the stars is parsec.
No, but these clusters have 1,000, 10,000 stars, even parsec. They're very compact. So it's not, in that sense, utterly crazy. It's just, do they really take 10 million years to form a star? That's the hard part.
Also, if you're in a gas cluster, would it slow down the wind?
Yeah, I mean, just be new, right? If you have a AGB star at the other end of the cluster, that's not going to get to you.
The cluster's only parsec.
Well, it's not the mass between you and.
Oh no. This is 10 million years after. There's no gas in it. Right? Clusters get rid of the gas in a few million years. That's what makes them hard to planet. So now you got to get that to anyway.
That's okay. All right, so just going on with this scenario for a bit longer. So just to recap where AGB stars make aluminum, they make it through proton capture nucleosynthesis, hydrogen burning, through these higher order burning chains. So these are also catalysts to hydrogen burning, but they produce negligible energy. So this is the main way that we make it, aluminum-26 through proton captures on magnesium-25. And if we look, so this is made again through this proton capture nucleosynthesis at the base of the envelope. This is a highly mass-dependent thing. So just to show, this results from a 4 solar mass model showing the 26 to 27 ratio, and this is time scale just during the AGB again, and the ratio reaches about 6 times 10 to the minus 4. But if we move to a 6 solar mass model where the temperature at the base of the envelope is much higher, we see that we reach a ratio that's almost 2 orders of magnitude higher, or 2 orders of magnitude higher, 1.5 times 10 to the minus 2. So that's why that's one of the reasons why we're interested in looking toward these more massive AGB stars, which is different to Wasserberg. He looked at the 1 to 3 solar mass. What about iron 60? This can be produced by neutron captures in AGBs. It requires quite a high neutron density, though, to overcome this. So this is the chain that makes iron 60. It has to overcome, this is what's called a branching point, an iron 59, which is unstable. So you need a high neutron density to bypass, to activate this chain. Otherwise, iron 59 tends to decay. So this means you need neutrons coming from this neon-22 alpha N source. So this is the main neutron source, or main neutron-producing reactions in massive stars, where the neutron density is typically 10 to the 10 per cubic centimetre. This also operates in the helium-burning shell of AGB stars. However, the main neutron source in AGBs, at least in the low-mass AGBs, is this C13 alpha N reaction. However, we don't think that has neutron densities that are much lower, 10 to the 7, 10 to the 8 per cubic centimetre. So we don't think that these could make neutrons to overcome this branching point here. This neon-22 alpha N reaction is expected to, it is efficiently activated in stars with initial masses over 4 solar masses. So that's also why we're looking to the more massive AGBs. Just to note, manganese 53 cannot be made by AGBs. It's proton rich, so it's only destroyed by neutron captures, nor iodine 129 or hafnium 182. These are R process only nucleides. You actually see the hafnium. Yep, that's right. It has a long half-life though.
That's coming from supernova.
Yes, yep, that's coming. That'll come from a supernova, or wherever the R process occurs. It's probably a supernova. So I guess so other people have looked at the AGB scenario, in particular Jerry Wasserberg, but he focused on the lower mass 1 to 3 solar mass range. Yeah, that's again one reason why we're not so much interested in the 1 to 3. There, I think the problems are exasperated. Is that the right word? Yeah, so whilst I find Jerry convincing, I'm not convinced on that one. Exactly. Exactly. Okay, so Jerry has this toy dilution model that we would like to start to play with. It's just parametric, very simple, which has 3 main parameters. It has the dilution between the solar system, or the giant molecular cloud, and the stellar material. It has a time scale, the time difference between formation of the injection of material and the formation of the first solids, and also the time interval between formation of the first planetary differentiates. So what we'd like to do is use something like this toy model with our AGB results to try and to possibly use this to differentiate between the 2 scenarios. We're not sure if it's going to be possible yet. We are only at the stage now where we're making AGB models that include isotopes up to, for example, palladium. So this just shows results from a 6.5 solar mass model of solar composition. So we had to extend our nuclear network to include elements up to palladium. We only have a few models that do that at present. Anyway, so this is the isotopic ratio between the radioactive to the stable as a function of thermal pulse number. This is a proxy for time, if you like, versus log of the ratio. So we now have some results that we'd like to plug into a toy model. And notice that we also have, I'm also showing at this lower panel, so this is shown as I guess as a difference from the solar ratio in parts per 10,000. So this is some stable isotopes. This is nickel-62 and zirconium-96. These are stable, but they're shown to correlate, their abundance is shown to correlate with iron-60 in refractory inclusions found from meteorites. So that's also something that we thought we could consider. So AGB plus supernova, again, that red really doesn't show up. So this is showing results from my models, so as a function of stellar mass, showing the yield of iron-60 to aluminum-26, and you can see now this ratio, which is all I really wanted to focus on, is greater than unity, whereas for supernova, it's less than unity. So this is why we're interested in comparing these models to the meteoritic data, to these ratios, and also to see if we can maybe find other radioactive pairs like iron-60 and aluminum-26 that we can also use as a discriminant. Notice also that our models stop at essentially 7 solar masses, where KEFIs start at 10. So there actually are no predictions from the 7 to 10 solar mass range. This is because these stars are really hard to model. They go through off-center degenerate carbon ignition before doing whatever they do. I could use all sorts of words to describe how, I mean, a hydrostatic 1D code really doesn't like to model these stars. People are starting to look at it now, but there's still no yields, there's still no production factors. So I have one model that I got through central carbon burning. This was more to look at composition of halo objects. So I was looking at, so this is stars with very low metallicities. But this went through carbon burning, so it has an oxygen neon core of 1.125 solar masses. This is just, again, the helium exhausted core, hydrogen core. This is the hydrogen envelope. So this one, it'll even though the core will keep on increasing, it'll probably lose its envelope before it reaches 1.4 solar masses and explode as a supernova. Now these stars probably won't they won't have an iron core, so when they explode as a supernova, if they do, so this could be the upper mass range, they're going to be electron capture supernovas. So they're going to be really very different to, the iron core supernova. They will have very different light curves as well. There's very few models of these stars around. I mean, I could probably name 5 papers that have modelled these stars in detail. There's only a couple that have even considered the nucleosynthesis so far. So this is just during the AGB phase, of course. I don't know what the final fate of this particular model will be. It'll probably be a massive white dwarf. So this is just showing some results for some hydrogen burning species. This just shows the effects of very hot hydrogen burning, essentially through the magnesium-aluminum chains. And just to note, the stellar lifetime of this is 4.3 megayears. So this is a fairly short-lived star. Stellar lifetime, did I say half-life or stellar lifetime? Right. Okay, so really, I guess this talks about future work. We haven't really done very much yet, but we've got many things that we'd like to explore. Certainly all the model predictions, whether you talk about low mass stars or supernova, have lots of uncertainties, whether it's the nuclear physics or the stellar structure. These need to be studied in the context of radioactivities. We have AGB predictions from hydrogen through to nickel. We want to extend this to S-process elements all the way up to lead. We've started to do that. We're up to niobium in some cases, in 1 or 2 cases up to palladium. So once we have some more models, we'd like to examine this. Once we have this toy dilution model in the context of our AGB models of a range of mass and initial metallicities, as well as take results from KEFI's and Lagrange's supernova models. And it'll certainly be a lot of fun to study those SUPER-AGB stars in more detail. It'll be really interesting to get some nucleosynthetic yields from these stars. And I'm going to be working with KEFI and Lagrange to try and maybe take my so I'm going to try and evolve it through the AGB and then give it to them, and they can try and then maybe hopefully explode it as a supernova. So this is, I think, going to be a fun project regardless of, I think, what happens. So in summary, meteoritic evidence shows that the solar system was pervaded by short-lived isotopes, many with half-life shorter than 2 megayears. Spallation reactions, certainly the source of some isotopes, such as beryllium-10, but not all of them. Iron-60 requires a stellar source. A supernova is certainly the most likely candidate. It does really, qualitatively, it fits the bill, but there are many quantitative problems. The high abundance of AGB debris is evidence of an AGB component, but it does not prove they were carriers of the live nuclei. If detected, so this is something that Wasserberg suggested, that if you could find lead-205, which is an S-process only isotope, and therefore it's made in AGB stars, it would certainly strongly support an AGB scenario. Also, better estimates of the iron 60 to aluminum 26 ratio in meteorites would help to constrain the models, as well as other isotopic pairs that could be also used as constraints. Anyway, that's it.
So in order to make the time scale work out better, you'd like to have supernova at the very low mass and as low a mass as you can get, and the HB at the highest mass you can get, and it's supposed to have a better chance of going off within half a mega or however close you like to go off to each other in order to contaminate us simultaneously. Now, just understand, it's the low end of the supernova. I mean, how well are those nuclear
are those masses
known? I mean, is it uncertainty, or is it well known? I mean, does it depend on knowing whether it can go supernova?
It's not known at all, actually. Yeah. The mass is not well determined. I mean, with that tends, I think, so if you look at Weasley's papers, any of his papers, or Kieffi's papers, they all started 10, 11, 12 solar masses, and that's because these are the stars that go through non-degenerate central burning stages, essentially. So they can model them relatively easily. And our models, we tend to go up to about 6, 7 because we can model those stars relatively easily. They don't go through central carbon burning. So it's really not well known what happens to a 9 or a 10 solar mass depending on where you're. I mean, even the mass that you choose that becomes a supernova, an iron core supernova, depends on the model details, and they're not well determined either. They depend on convection and carbon-12 alpha gamma reaction rates and all sorts of things. So. Exactly, they're just an idea.
Natasha argues that you need these things to produce the LMXPs that you see in black clusters. So there's some motivation for that observation. Yep. Theoretically, none of this stuff is when I guess there's observational support that certainly the lower mass range turn out to be oxygen neon white dwarfs, because we do find that there are observations of very massive white dwarfs in the galaxy that are probably of the order of 1.2 solar masses. These are white dwarfs, they're not neutron stars. So these stars probably do come from that lower mass range that go through central carbon burning. So we know that some of them become white dwarfs, but it's not clear where that cutoff is, or if they even do become electron capture supernova. There's another problem which Wade was alluding to. So even if you have a cluster where you have a lot of stars that include supernova and AGB stars together, of course the sun didn't form in that cluster because that cluster lost all its gas 7 million years ago. There has to be another region where the sun forms nearby. So this is like now, of course, it is true in giant electric clouds, right? You see, like in Carina, there are 12 star clusters, but they tend to be sort of, the nearest pairs are sort of a few parsecs apart. Right?
That's getting far.
Yeah, that's getting far. Well, of course, if the supernova goes off after you have an AGB wind, it can sweep up the AGB.
It goes one way, so supernovas will benzene before.
Well, not necessarily. There is a spread of order 1 million years in the ages of individual clusters stars. So you can imagine that you form one of the AGB stars before you form the thing that eventually becomes a supernova.
What is it?
You got to be. You're near the cylinder. Yeah, exactly.
Is it possible it's the same star that gives both the AGB and then the supernova?
If it was, well,
really massive stars tend to have Wolf-Rayet
yeah.
winds. They're too luminous.
Yeah.
So
They don't go through an
by, UV-driven winds.
80 solar masses, so 40 solar masses is probably the cutoff. No. Well, they don't really. They do. Well, they have some winds, but the thing is that they don't go through. They don't make that slow neutron capture. They don't have slow neutron capture nucleosynthesis, or at least that they don't that makes elements between, say, strontium and lead. And that's where you need the AGB component to make something like palladium-107 is quite easy to make in an AGB star. You get this it's called the weakest process in massive stars, but that tends to make elements from iron up to strontium, but nothing really much after that. So you can't. Yeah. You still need a component of S process. So.
There's no mass star which has uses both the AGBs.
Well, possibly one of these electron capture stars. If it becomes an electron capture supernova, it would go through a thermally pulsing AGB phase first, where it would have that slow neutron capture nucleosynthesis. But then, if it explodes then as a supernova, it might also then produce all the stuff that supernova produce as well. It's actually it's not clear really what they produce. So,
Iron is 60.
they could produce it through the slow neutron capture process.
Yeah,
So-
you were arguing you can actually do that.
Yeah, you can. You can. I mean, you can see from. I mean, I had some. I mean, in those yields I showed,
Okay, so
we can
then
actually
you
make it. So,
Then you don't need a core top supernova at all.
not to make iron 60, no. To make manganese 53, you do, for example. 'Cause that's a proton-rich isotope. Very hard to make. You just can't make it. It's destroyed by neutron captures only,
Well, but
for
can
example.
You do it you wouldn't do it in a pair.
In a pair production.
Capture.
It depends on if the R process occurs. If it's like if something like the P process and the R process go together in that sort of supernova, then you could. So it's really
That would make life a lot more pleasant.
If one chooses the thing of thought of both.
well. Certainly, I mean, if you look at pre-solar grains, it certainly shows that the R process and P process nuclides are correlated together. So if you look at, say, the xenon isotopes, you tend to find in say pre-solar diamond grains, I think you tend to find if something's enhanced in an R process xenon, it has also P process xenon as well, which is also enhanced. So that shows that the two tend to go together, basically.
Which sounds like it's coming from the same source.
It sounds like it's coming from the
So it
same
sounds
source.
like
Yeah,
there needs to be more work done on these intermediate mass stars.
I think so. Yeah, and that would be that's
So
kind
who
of
does
fun.
this sort of stuff? Like Latanzio? Does he do?
He does do some of this. There's also a guy in Belgium, Lionel CS, who started working on these SUPER-AGB stars as well. There's also Chris Tout's group in Cambridge who's also interested in doing some of this work. I think Kiefi is vaguely interested in it. I think he's interested as long as he doesn't have to compute the AGB part. He's not interested in really doing that anymore. So there are some people who are interested in working on in doing these in modelling these stars. So.
Okay.
So.